Hi there, my name's Dr. Kai Clark, and this is going to be a second of two lectures. So I've prepared two lectures on time synchronisation and clock synchronisation. The first one was more on the fundamentals of clock and time synchronisation, but this second one here is much more focused on types of clocks and oscillators which you might see used for synchronisation, as well as different standards that you might see used for synchronisation, particularly focused on ones used in the data center, in particular the Precision Time Protocol, or PTP. I've been able to record this partly through the support provided through my research fellowship, which I'm doing with the Royal Academy of Engineering. So allow me to show you my slides. So here we go. So clocks and standards, time synchronization in data centers. So let's start with the types of clocks you might see. So we've been through fundamentals last lecture, so now you know the basics, and some are more slightly higher than basics. So these are the sorts of oscillator you might see. So quartz oscillators are the most basic type, and they are everywhere. They're from everything to my watch here, kindly given to me by my dad a number of years ago, to expensive types of crystal oscillators which are oven encased. So let's go through some of the different types, but first, all of these are based on what's called the piezoelectric effect, which is where if a precisely machined quartz crystal is subjected to a specific frequency that's applied with some oscillating voltage, it resonates. So if you subject it to the correct frequency, then the resonant frequency will mean that the quartz crystal will vibrate more strongly. And if you're off, it will vibrate not so strongly, so you can lock a circuit to that piezoelectric vibration. So there are many different types, and a lot of different companies make these, and there is everything from the sort of basic crystal oscillator that you might see in a watch. Those are extremely cheap, so you can pick those up from, say, Farnell for under 5p. Through you get increasingly complicated ones. So you also get crystal oscillators where there's some control over the voltage the crystal is being subjected to, because the frequency, resonant frequency, will change with the voltage you apply, so you can have some compensation and control for that. You also, above that, get crystals that will include a thermistor, which will measure the temperature of the crystal or the environment around the crystal, so that the resonant frequency change with temperature can be compensated for. We often call these TCXOs. And then if you go a step beyond that, you start looking at what we call oven-controlled crystal oscillators, which is where you take your crystal and you put it in an oven, so that it's put up to a known, usually quite high temperature, so on the order of, say, 70 degrees C, much above what the environment might be. And then sometimes, in some cases, you will even stick one oven inside another oven, and this inner oven contains the actual crystal. And in terms of costs, these most advanced, like double oven controlled crystal oscillators, these can be over £150 potentially. And the key thing is you've got a real stability versus power, size and cost trade-off. So the further down this list you go, the more stable the crystal oscillator is, but also the power consumption of the oscillator goes up. Its size will go up. If you look at these packages, this is fairly big. This is on Vero board. This is about that large. The double controlled oscillators are even bigger. They can be like this big. These are smaller. It's about like this big. And then the smallest basic crystal oscillators can be as small as tiny package, like one you might see in a watch, for instance. But the performance of double oven controlled oscillators over long time periods still doesn't beat the other way you can synchronize time, or one of the other modern ways you can do it. So you can use atomic clocks, or specifically we're talking about the traditional microwave based atomic clocks here, So what these all do is probe what we call the hyperfine splitting of energy levels in a collection of atoms. So what this means is that when you put atoms in a magnetic field, the electron energy levels around the nucleus begin to split. And what you can do is you can fire microwaves at those, and you'll pip the electrons up into a slightly higher state, and then they'll fall and release energy. And what you can do is you can lock the frequency of some oscillator, usually it will be a quartz one, to that energy transition. And in all of these clocks end up being more stable at long time scales than the crystal oscillators over here. And there are again a lot of variety in this area. So you've got everything from chip scale atomic clocks, or CSACs. These are quite small, so these are typically about this big. To you go up a bit bigger and you can go to, say, rubidium clocks. These are usually about way big. And then you start going up to cesium beam tubes. These are about this wide. These are designed to fit into a standard rack unit. And then lastly, you get these massive cesium fountains, which you typically see in the National Timing Labs, for instance, at MPL. And in general, with all of these systems, the bigger they are, the more stable they are, because population of atoms goes up, and you can also use more tricks like let them fall under gravity, etc., which gives you a better and more stable measurement. But this also means that although you're getting better stability, the cost also goes up a lot and the size goes up. So in terms of cost, the hope is that in the future chip scale atomic clocks might go under £1,000 as more and more manufacturers make them. At the moment they're very much targeted at military applications in particular. Then we've got our rubidium clocks. These are more stable than the quartz oscillators, for instance. These would typically run you about £2,000. Then you've got your cesium beam tube atomic clocks. These are a lot more money, so these we start running up into £100,000. And then lastly, our cesium fountains here are very, very expensive. There are commercial cesium fountains you can get, but nonetheless they're in the millions of pounds range. And typically the highest quality clock you'll see in a telecoms environment is usually a cesium beam tube. You don't see cesium fountains in a telecoms environment usually, because they're just too expensive and not considered necessary under current standards. One crucial thing, which is quite cool, is that we define the second based on cesium. So we define 1 second using the cesium unperturbed hyperfine ground state transition frequency, as we call it. And that's actually how we define the second for our definition of time worldwide. But on that topic, that might change. So there are a number of types of clocks that are still under research, or alternatively just not used in telecoms at all. So firstly, we've got our optical atomic clocks. So these are very cool. So the idea is that instead of probing the hyperfine splitting of energy levels, you can probe what's called the fine splitting of energy levels. So this is a much bigger energy difference, and you can use light instead of microwaves to lock to this transition. The amount of fundamental noise from this transition is a lot smaller, so potentially you can get much higher accurate clocks, higher accuracy clocks. So cesium optical lattice clock, for instance, under research at places like the University of Birmingham, as well as NEST, are as much as 3 or 4 orders of magnitude better than even hydrogen masers, which are on the right hand side here. And this also translates down into smaller, more commercially focused sizes. So these benchtop strontiums will probably eventually define the second. There might be another atomic species that's used, such as ytterbium, but nonetheless at some point agreement will happen. But going down the size more into commercial products that might be used in telecoms, you've got your rack mount atomic clocks, For instance, there's Tictor by Inflection have made a commercial unit, and then we've also got chip scale atomic clocks, which could be even smaller, so based on this optical transition. And it's probably likely that eventually these will be used in telecoms networks in the future. And then we have another sort of clock. So these are hydrogen masers. And these fundamentally probe the energy that's required to reverse the spin of an electron that's in a hydrogen atom. So electrons and protons have spin. And this is kind of a weird concept. It's like their quantum mechanical spin. They can rotate in one direction or they can rotate in the other. And they're either aligned with each other, i.e. spinning in the same direction, or one spinning one way and one spinning the other. It's difficult for me to move my fingers to do that, but essentially they're rotating in the opposite direction rather than with. And there's an energy difference between these two, and you can lock some oscillator to this in the same ways you can with the atomic clocks. There are two types. There are active hydrogen masers and passive hydrogen masers, and they are very expensive. So they're at least £200,000 to potentially over £5 million each. And they're mostly used in metrology laboratories such as MPL, and they're also used in global navigation satellite systems or GNSSs, such as GPS Galileo. But they're not used in telecoms, mostly because they're far too expensive and they're also very vibration sensitive. So if you knock them, they will go off frequency. So they tend to serve quite specialised needs. Nonetheless, they are very, very accurate over long time scales. So then we move away from types of clocks and how we start linking clocks together. So ideally, one would think, well, you build a network and every single clock will be the best clock you possibly can have, i.e. you stick cesium rack mount atomic clocks everywhere. But clearly that's not very practical. Most companies do not have £100,000 to spend to put a cesium atomic clock at each base station, for instance, if, say, we were EE or another telecoms company. And on top of that, the power and size of them is just too big to be practical. So instead what we do is we have a hierarchy of clocks where we have subordinate poorer quality clocks that are synchronized to higher quality master clocks. And so what's quite typical in telecoms and in data centers is you will lock to some source of time. In many cases it's GPS, and that will be connected to some time server that will serve as a primary reference source, or PRS. Typically you'll have a very nice clock there. So you might have a cesium, you might have a rubidium, maybe, depends on your cost against stability considerations. And this is the highest clock in the hierarchy. And then you'll synchronize a nice clock, but not a very, very expensive clock, maybe something that's really quite inexpensive, like £150, such as a double oven controlled crystal oscillator, or DOCXO, to that cesium. You might have several of these. You probably won't just have one, you might have like 10 or more, all synchronized to that cesium. You then go down in cost a bit more, and so you go to an oven-controlled crystal oscillator, not quite as good, cheaper still than the DOCXO. And then lastly, you're getting thousands upon thousands of nodes, and at this point you really need to keep costs down. So now you go towards temperature-compensated crystal oscillators, which are small, relatively inexpensive. And when you get right to the endpoints, maybe you probably just use a simple crystal oscillator. So essentially, as we go down this tree, the accuracy is getting poorer and poorer. But that's okay, because we're locking these clocks to a really, really nice master clock, or primary reference source. So there's a term called clock strata, which we often use to represent this. So the idea is the further a clock lies from a source of absolute time and frequency, the poorer the clock and time frequency accuracy. So this is represented as stratum levels. That's especially true in the network time protocol, or NTP, which is standardized in ANSI T1.101-1987. And each stratum, the number specifically, depends on two things: the quality of the oscillator on each node. Certain strata have minimum requirements for quality of oscillators. as well as the number of hops away from the source of absolute time or frequency, denoted as stratum 0. So, for instance, either a GPS or the cesium, if GPS goes down, would be your stratum 0. And then that's connected to a time server, which will be stratum 1. Typically, you'll need a very nice clock to meet stratum 1 classification, something like a cesium. And then a stratum 2 is synchronized to that. Typically, that'll be a DOCXO. And then a stratum 3 is connected to that, probably looking at an OCXO for stratum 3. And then lastly, for stratum 4 that's connected to that, probably looking at TCXO. Again, the time accuracy is going down as you go down the chain, and this can go far beyond stratum 4 as you connect to more and more clocks downstream. So then we have an important concept called holdover, a very important concept in both data centers and also in telecoms networks. So consider a network that you source from GPS. What happens if GPS goes down? Say there's a huge solar flare and all the GPS satellites are knocked out for, hopefully not forever, but say they're knocked out for, say, a month. What do? This, of course, is very unlikely, but it's always possible. And there are much more likely things that can happen and do happen, such as GPS jamming is quite common for numerous reasons. It's a very small bandwidth GPS, so it's very easy to block the frequency. Also, you can get much smaller solar flares. Relatively recently, earlier this year, GPS was interrupted temporarily for about a day, and tractors in the US were parked at the edge of their fields because GPS relied to find their position, and they couldn't do the mowing and the tilling and the things that tractors do. So it's good to have a backup. So this is how you have the backup. So if GPS fails or whatever, while it's down, you get your reference from the best clock in the hierarchy. So you get it from your primary reference source. And this primary reference source needs to continue to act as some accurate source of time for some holdover period during the interruption of this time source. And what inevitably happens is the time source drifts. So it moves off the absolute frequency as a function of time. And you can measure this by just locking the frequency source and then just turning off the lock, but continuing to measure against the original source. You'll get the drift that way. So the degree to which drift can happen is defined by standards. So for instance, in the enhanced primary reference timing clock standard, or EPRTC G.8272.1, this defines the maximum allowable drift in holdover. So for instance, for an EPRTC clock class A, the maximum drift that's allowable is plus or minus 100 nanoseconds over 14 days. And the minimum that it must be before it goes into holdover is plus or minus 30 nanoseconds. It has to be within 30 nanoseconds absolute time from its source. So, one last thing on this. This also applies for every single point down the chain. So, GPS going down is a rather major thing. That's that's not very likely. But more likely is something like, say, someone unplugs a cable in the data center, and there's a bunch of clocks that suddenly lose access to time. So these clocks that are further downstream will have a smaller time holdover period that they need to remain stable for, so that these servers at the end, for instance, don't wander too far away from what absolute time is. The further up the strata, the closer you get to the primary reference source, the more stringent the requirements on holdover are, and you can find those in those standards. So then we get into factors affecting accuracy, and I'm preferring to introduce things this way round because it helps people to understand why different timing standards are limited in the way they are, and why they're used in certain places and why they're not used in others. So the first thing that's really key is that when you choose a time synchronization standard, it is really a trade-off between the amount of inaccuracy you can tolerate against cost and component complexity and the specific equipment you have available. So consider what factors impact that accuracy or the time offset. So you've got a number of different factors, and these are going to um, decrease in their impact on inaccuracy. So firstly, if you use one-way timestamping, so you don't do any measurement of the delay, then the impact on accuracy can be anything from nanosecond order to hundreds of milliseconds potentially if you go for a longer distance. So the things impacting that are going to be the distance you're sending your timestamps over. It's going to be your network complexity. The bigger these two things are, the worse your accuracy is going to be. The next thing is going to be your delay asymmetry through software buffers and queues. So say you're running, say, TCP and packets are spending a lot of time in a TCP buffer, you could be getting milliseconds of accuracy impact from that. Then the next factor is, if you deal with that, you've then got to deal with the fact that you might have two paths which are different lengths. So say you go from London to Birmingham via Manchester for one path, and for the way back, you go direct from Birmingham to London. This might sound a bit silly, but this does happen sometimes. Sometimes the routes going one way are very different to the route going the other, and the impact from this can be anywhere really from picoseconds to microsecond order, and the bigger the length difference, the lower the accuracy becomes. And if you solve that, the last thing then becomes that you have delay asymmetry fundamentally in the digital hardware you use. So your hardware itself, the serial transceivers, the various flip-flops, etc., their variation with temperature ends up limiting you. And that's on the order of nanoseconds to tens of nanoseconds. It all depends on the hardware. So how do you fix these? So to deal with one-way synchronization, you use two-way synchronization. That fixes the problem. You measure the delay. To deal with delay asymmetry, you use hardware timestamping. You don't do things in the software layer. You move away from that to a hardware implementation. To deal with delay asymmetry from mismatched paths, now this will start to get more impractical. You transmit in both directions through the same fibre. So you transmit one way and you transmit the same way coming back. Or you're very careful to make sure that your fibres are going down the same channel or path that will also get closer, although not as good as this. Then the last factor, this delay asymmetry, at this point you really have to start building very complex hardware to measure and compensate for the difference. People have done it, there are commercial standards to do it, but it is difficult and it can be more expensive. Though maybe one day it will be about the same as PTP, for instance. So then we have the various factors that impact precision. So remember, this is our distribution of the points. So what affects this? So you've got the stability of this one-way delay. So say you don't do two-way timestamping, you just do one-way. So the precision impact could be nanoseconds to milliseconds, and it's again all dependent on combination of the distance and the network complexity, and the amount your packets might suddenly start going a different way. For instance, if you're going from London to Japan or something like that. And that will impact your precision potentially quite substantially. The next factor, the stability of the delay, is what stability of delay you've got through software buffers and queues. So you might send a packet two ways or one way, and your queue variation just varies. Your CPU happens to serve some packets sooner than others. Impact on that could be as big as milliseconds. And then if you solve that, you've got the fact that whenever you timestamp, you're always going to get some drift of the clocks between two timestamping synchronization steps. It's like, say myself and a friend synchronize our watches on Monday, and we synchronize our watches every Monday of once a week. And if our watches aren't very good, what we might see is that by the time we resynchronize, my friend's watch might be a few seconds faster than my watch, or vice versa. However, if we measured much more often, if say we measured every day, that offset would be smaller, right? It might be a seventh of a second or something like that. So what this means is the faster we do our updates, faster we do like our synchronization steps, typically the better the precision becomes. The smaller we do our updates, the worse it becomes. The other thing is that if you've got a lot of network load and you're running a system where you're doing timestamping, that could delay your packets, and that will also potentially impact your precision. Because you might not be able to send as many of your synchronization packets through, which could impact your rate. So then lastly, you've got the medium itself. No medium is static. Fibre varies its time of flight against temperature by not a tiny amount. It's about 10 billionths of a second per kilometre per degree C. So if you consider that a fibre that's outside might actually change by quite a lot, it could be 10 degrees C or more day to day. That impacts your precision as well. That can be anything from picoseconds to tens of nanoseconds. So now you know you're getting into the point where you've solved the other problems, but fundamentally your medium limits you. So then how can you mitigate these things? So for one-way delay, use two-way timestamping or synchronization. That solves that problem. You can use hardware timestamping to deal with the stability of the delay through software buffers and queues. If you want to deal with the clock frequency drift, you can use either better clocks that are less sensitive to their. You can use better clocks that are less sensitive to their environment. But what you could also do is you could use faster timestamp exchanges. You could exchange, say, 100 times a second instead of once a second, etc. If network load is a problem, if you've got a lot of traffic on the link you're doing your synchronization on, you could somehow lower the traffic or use higher bandwidth links. If you solve that, then ultimately the only thing you can do about the transmission medium is use a different transmission medium, or make it more stable by encasing it somehow to make it more stable. So for instance, if you're operating optical fibre that's hung between telegraph poles, you're probably going to have a less stable medium than if that fibre is buried underground, for instance. You will see a difference for sure. So that's that. So now we move on to standards. So you understand the basics. You understand how you do one-way synchronization and two-way synchronization. You know what the impact of a different synchronization methods are. So let's go through the ones which you typically see. This is all for time sync. There is one frequency synchronization standard I'm going to briefly go through as well. But the first one is this one, the Network Time Protocol, or NTP. This is a two-way synchronization protocol, and it runs in the software layer. It's low complexity. It is typically used in wide area networks. So in, for instance, your typical network run by a big telecom company spanning the UK might, for instance, use this protocol. Its accuracy is on the order to milliseconds to hundreds of microseconds, and that's about hundreds of milliseconds, and that's really limited by variable software delays as well as any asymmetric network delays which are present in the system. If, say, one way your packet goes up to Birmingham via Manchester, and the other way it goes directly to Birmingham, directly from Birmingham to London, say. Then there's a subset of NTP called the Simple Network Time Protocol, or SMTP. This is a one-way variation, so it just sends packet one way to synchronize time downstream. It's again software layer only. It is very low complexity because you're just doing one-way timestamping in the software layer. Its accuracy is quite poor, so it's on the order of milliseconds to seconds. Keep the key limiting factor varies combination of the software delays, and there's also no delay measurement. I believe that there are also ways to run the network time protocol using hardware timestamping as well. I don't know the degree to which NTP is accurate running in that mode compared to PTP, but nonetheless that may be worth looking into if it's supported in the hardware that you're using. Before we get on to our main focus, I'll just mention White Rabbit. So this is a two-way synchronization protocol. It requires, however, specialised hardware and specialised optics. I'll also note that White Rabbit logo is property of White Rabbit. I do not own the copyright on that. That is theirs. So this protocol requires specialised hardware and optics. It was developed at CERN. It's used in particle accelerators. It's used in radar, etc. And this is accurate to sub-nanosecond level, so it's the most accurate standardised method of doing time synchronisation there is currently. And this particular method ends up to a point where you're almost entirely really limited by the medium. So what we call fibre wavelength dispersion, which is that some wavelengths of light travel faster than others. The variation in the laser wavelength can give you an accuracy there. And also that you still have, even with White Rabbit, some residual asymmetry in electronics. That can be a problem. But our focus for the rest of this lecture, other than synchronous Ethernet, which I'll briefly go through, is going to be the Precision Time Protocol, or PTP. And this is a one- or two-way synchronization protocol that runs in supporting hardware in the medium access control or physical layers. So it's not in the software layer. It's used almost entirely in local area networks, including in data centers. It's not really used in WANs. I think there are some exceptions out there, but by the by, not used in WANs. Its accuracy is on the order of nanoseconds to microseconds, so it's much more accurate than NTP, especially versus SNTP. The limiting factors on it are ultimately asymmetry through separate fibres, if your network is running in that way, and also the digital transceivers end up limiting you, as well as the resolution that the clocks can be measured at in the receivers and transmitters. So before I talk about PTP, I just want to talk about SYNCI. So this is a further common standard you might come across. So SYNCI is short for Synchronous Ethernet, and this is not a time synchronization standard. It does not synchronize time. What this provides is a continuous frequency reference that's carried through some hierarchical Ethernet network, specifically Ethernet, hence Synchronous Ethernet. SYNCI is much more commonly used in telecoms networks versus data centers, to my knowledge. But it's still important to be aware of it, because you might wonder what it is and how it differs from PTP and such. It is completely compatible with, and very often runs alongside PTP and or NTP. Well, not and or. You'd really use one or the other. It will run alongside PTP or NTP. So this is how it works. So in Synchronous Ethernet, you've got the clock frequency embedded in data that's transmitted between each node. You've got some hierarchy of clocks. So you've got some grandmaster clock that's locking to a source of absolute frequency, and this frequency is received by some GPS receivers, say, and some cesium clock typically is going to lock to that frequency, so from GPS. Then that cesium clock sends out its frequency, and it sends that, and it's used in the transmitter that's pointing downstream to your next node to encode the data. So the clock's embedded within this data, so clock frequencies within there. That then arrives at your receiver, and it's processed by a clock and data recovery circuit. And then the same thing happens. That clock and data recovery circuit recovers the clock, draws the clock out from that data stream, and it feeds it into its oscillator. Typically it would be a worse oscillator than the previous stage, and that will lock the frequency of this oscillator to this upstream one, and then that will output its clock. That goes into another transmitter, which embeds that clock frequency within data that it's sending, and that then is used and extracted from that data when it arrives at the next node at its receiver by its clock and data recovery circuit. That synchronizes the frequency of its clock, which it then sends onwards to its transmitter, it sends it onwards, etc. So you end up with this long chain where everyone's frequency synchronized based on some original clock. Now, remember I taught in the last lecture that you can synchronize frequency with timestamping. So that is true, but the issue is drift. Your oscillators will drift between you doing these frequency synchronization steps. This is better because you have a continuous source of clock frequency. You are always seeing the frequency, not every, say, every 20 milliseconds, best case, if you use the maximum PTP synchronization rate of 128 Hertz. But there are downsides. The first is that you can get what's called jitter accumulation. So when you embed the clock within this data, a clock embedded in data is always going to be poorer quality than a directly transmitted clock. That's pretty much fundamental. If you look at the frequency, essentially, if the power of that frequency, essentially it will always be lower than if you just directly sent the clock out as, say, a continuous set of ticks. So what can happen is the jitter accumulates here. The jitter ends up being passed through to this oscillator, and then you pass that jitter through into the next transmitter, which then gets even worse here at this third stage and even worse at this fourth stage. So for this reason, what these systems end up doing, I haven't shown it in these diagrams, but they use what are called jitter attenuators, which are essentially very, very low frequency phase lock loops, which essentially almost retimers, like a way of locking a clock to another clock, you could think of it as, and they can help remove that jitter. However, they introduce something called wander, which is that over time your clock kind of shifts about. Nonetheless, Sync works well. The other issue is that hardware complexity goes up because you've got to take out this clock and output it somehow and use it to directly feed into a clock, rather than having some sort of a digital adjust your clock frequency up or down control. What this means in a commercial sense is you end up with less prevalent vendor support versus PTP or NTP. I think most devices will support PTP these days. Pretty much everything will support NTP because it's software layer, but Sync is less common. So that's Sync, also important to know about. But my focus for the next rest of the lecture is going to be PTP. So this is the Precision Time Protocol. It is a packet-based synchronization protocol, and what it does is it distributes clock frequency and time over a packet network. Typically Ethernet, but doesn't have to be. And synchronization packets, this is key to note, synchronization packets in PTP coexist with data traffic on the same network. And PTP is standardized in IEEE 5088. The latest amendment was this year, 1588E 2024. And here's an example of where you might use it. So this is the Open Compute project, one element of that. So this is related to Meta primarily, the synchronization of their data centers. So this is some PTP time synchronized data center network, and you've got three layers here. We'll go from the bottom upwards. You've got your server layer with your ordinary clocks. We'll get into that shortly, as well as these other terms. Then you have the network fabric. So you've got your leaf servers here, or your top of racks. Then you've got the layers above that. And then finally you've got your spine switches. And then these spine switches are all being time synchronized by grandmaster clocks, which are getting their source of time from GPS. Typically you'll have a few antennas on the roof. Well, you might have them in the building, depends on how much GPS is being blocked by going through your roof. And that's how you might do that in the data center. And then the key question then becomes accuracy, and usually we care most about relative accuracy, not absolute accuracy in PTP, because PTP is a LAN synchronization standard. It allows for nanosecond to microsecond accuracy within a LAN by performing two-way timestamping in hardware within the MAC or the physical layers. What I mean by the accuracy is relative is that PTP synchronizes all the clocks within a LAN to nanoseconds to microseconds of each other. That doesn't mean they're within nanoseconds or microseconds of absolute time, i.e. MPL's time. This is ultimately limited by the absolute source of time that the best PTP clock is synchronized to. Usually it's relative accuracy within a LAN that you care about most, for instance, scheduling data or for coordinating when you stop talking to one base station using your phone and when you start talking to the next one. The base stations just need to be have relative synchronization with each other. That doesn't mean it's not possible, though, to synchronize to good accuracy to an source of absolute time. So, for instance, you can get within hundreds of nanoseconds of absolute time, such as UTC MPL. You can lock to GPS at a lock to GPS time using GPS, but it is subject to potential loss of service. If you have a solar flare, you need to make sure that your clocks can hold over for that period and still provide good quality time. And the other thing is that time as a service over optical fibre is really attracting substantial commercial interest now. So, for instance, in the UK, we have MPL time, and that uses PTP to distribute UTC MPL to data centres in both Reading and near Canary Wharf. This is particularly of interest for the banking industry, who need to keep quite strict time requirements for financial transactions. Another thing you can do is, instead of locking to GNSS services, instead you can lock to what we call low Earth orbit satellites, or LEO. So these are LEO position navigation and timing, or PNT services, and they include Iridium STL is quite a big one at the moment. So the key thing about this is the power is much higher. So the power of GPS is very low because the satellite's very far away from the Earth. But satellites in low Earth orbit because they're so much closer, the amount of power that's reaching the Earth is a lot more. It's as much as 1,000 times more. So this means that you can achieve sync in environments that would be difficult in GPS. So, for instance, you can get sync within a building. I remember seeing LEO working at a conference. I think it was actually Iridium STL. I could see Iridium STL working in the middle of a massive hotel in Antwerp, and it worked. It was quite cool. So that is something else that is an option versus GPS. And because the satellites are within the ionosphere, they're more protected from solar flares than the traditional GNSS approach. So then we get on to network structure. How do you build a PTP network? So you build PTP networks by having a chain of clocks in a hierarchy. When don't you? I mean, all synchronization networks use this approach. So what types of clock are there? So firstly, there are grandmasters, or GMs. These are PTP time sources. They head the hierarchy, hence grandmaster. They are only master clocks, or MC, which is another term you may see. And these connect to all these other types of clocks. So at the very other end, I think I'll go through this one first, you have ordinary clocks, and these are endpoints. These are devices that you need to synchronize with time, actually care about doing something with it. And these are always subordinate to a master clock. And that might be a grandmaster or a boundary clock, which I'm about to explain. A boundary clock is both a subordinate and a master clock. And what that means is it sits between the two. So it will use PTP with packets flying to and from to synchronise its time to some grandmaster, and then it in turn will act as a master clock to ordinary clocks that are further down the system. And it acts a little bit like a router in that it divides the PTP network up into regions. So you can see that here. So you've got a region between the grandmaster and the boundary clock, and then you've got another between ordinary clocks and a transparent clock. I'll go through that in a minute. And the other thing is PTP coexists with other traffic. So you can see that here. There's some other data packets flying through your system, but the PTP packets coexisting with them. So lastly, what's this transparent clock? So PTP packets pass through these on the way to subordinates, at least in one of the two modes of using them. There are two, E2E and P2P. I'll go through both. It acts a lot more like a switch in that it forwards the PTP packets, and it doesn't have a concept of time. It does frequency synchronize itself to match the master, but it doesn't actually have a clock in the sense of it's recording the time usually. So that's typical structure. Then we have, what do PTP messages look like? So they can be sent in one of two ways, depends on how you build the system. So they're either sent on layer 2, which is the data link layer, so i.e. They won't pass through routers on different subnets, they need to be all on data link. So in this sense they pass through as Ethernet frames, they're sent as frames. Or you can operate PTP on layer 3, which is the network layer. In that mode, you send them as UDP datagrams, and PTP supports both IPv4 and IPv6, so you can do it with either of the two internet protocols. So this is what frame looks like. The layer 2 is a bit simpler, so I'll go through that first. So you have the two components which, strictly speaking, aren't part of the frame, but are present, and it's important to know these are present because of how timestamping is done. So firstly, on this far side you have an interpacket gap. So this is the gap that you always have between two successive Ethernet frames which are arriving at a receiver and being transmitted from a transmitter. These are always a minimum of 2 bytes long, although it does vary depending on the specific Ethernet standard. These can be longer, shorter. I think actually they're always longer than this, but either way it really depends on the standard, but that doesn't matter too much. Then on the front of the packet you have what's called a preamble. This is for synchronizing the clock frequency in the clock and data recovery circuit to the incoming packet, and it's also used as a kind of warning that the packet's going to start. But the big thing in this regard is there's a starter frame delimiter, which is 1 byte long, that says packet begins here. And then moving on from this, we've got standard components of the Ethernet frame. So we've got our destination MAC address, so this is where the frame needs to be sent. And then we have the SMAC, or source MAC address. This is the source of that frame. Then we've got a VLAN tag that's used mostly for QoS, I believe. Then finally we've got the Ethernet type. This is one of not finally, but then we've got the Ether type, and Ethernet frames for PTP have a specific reserved value of 88F7. And finally, within the standard structure, we have the cyclic redundancy check, which is used to check to see whether there have been any bit errors that have arisen in the packet. It's essentially a CRC when you transmit is the XOR of the entire packet. It is possible for you to get errors in both. That's very bad, but you build your system such that that doesn't happen. That's what Ethernet standards are all designed to avoid. So then lastly we have the bits which really matter for PTP, and those are the PTP header. I'll explain what that contains shortly, as well as the PTP body. Then we have the datagram variation. This is almost exactly the same with a few small differences. So the Ether type is not 88F7 in this case. Instead, for IPv4, it's a standard Ether type for IPv4, which is 0800, and if it's an IPv6 packet, it's 86DD for Ethernet type. Then on top of that, you have the IP header, so that will contain source and destination IP addresses as well as other content, and you'll also have a UDP header to indicate the standard ports for PTP. I'll state very shortly, and then we have the same two components. An important thing is, remember that I said PTP is done on the hardware layer, so this starter frame delimiter indicates the beginning of the frame, right? Or the beginning of the UDP datagram. It's important because it is the time of transmission or reception of this sequence in the physical layer or the MAC that's used to create all timestamps in PTP, everything. It's based on when this leaves for a transmitted packet and when this is received for a received packet. You need to have a consistent place, or the entire system won't work, and you'll get inaccuracy purely from not knowing when exactly to measure. So let's have a look at this PTP header first. What does it do? So it is 34 bytes in length, for starters, and it contains information about the type of message and any corrections that need to be made. The key content that you should be aware of is, firstly, it has a message type. So there are different types of PTP messages that do different things, and we'll cover all of them. Some in more detail than others, but nonetheless. So some examples are, you can have sync packets, delay requested packets, follow-up packets, and delay response packets. These are all given different numbers. You can all see them in numerous information that's said online. Key thing though is that messages that contain timestamps are called event messages, and by default these are sent on port 319 when you send PTP over UDP, so i.e. you're doing PTP on through layer 3. Messages that don't contain timestamps are called general messages, and by default they're sent on port 320, sorry, when you're sending PTP over UDP. Then we've got some others. Version of PTP is simply the version you use. I think current version is 2, so that's standardised in IEEE 1588 v2. And then you have the message length. This is the length of the entire PTP message, so body plus header. Then we have the domain number. This is used to create separate PTP hierarchies on the same network. This is quite a lot like VLANs, if you've ever worked with those. They're like virtualized networks where things aren't supposed to be able to communicate with each other. And then you have correction fields. So this is quite important. This is used to stick the correction for the path delay. It's used by transparent clocks mostly. So then we have the PTP body. So general messages might not have a body, but event announce messages do. They contain information about the clock that's transmitting the message. Event messages, so sync, delay request, etc., carry PTP timestamps in their PTP body. In PTP v2 event messages, the timestamps and hence the PTP body are 12 bytes long, and they contain the time of day. And the time of day is not defined as UTC. This can trick people up. So it's defined according to what we call the Unix epoch in International Atomic Time, or TIA. And that is the number of seconds since 1st of January 1970. So for instance, at the beginning of January of 2024 at midnight, it was 1,704,067,227 seconds after the 1st of January 1970 at midnight in TIA. And you'll notice the 27 there seems a bit odd. It's not a very round number. So the reason for this is that UTC has leap seconds applied. The Earth is slowing down very gradually. So UTC runs behind International Atomic Time due to that. And there is a lot of debate over whether leap seconds will stop being used. Most likely they will stop being used because they, in particular, cause a lot of grief for people that own data centers, because you need to smear out the second, essentially, when the leap second hack happens. But nonetheless, it's a digression. How do you store the time of day? So you store it in this way. So you have the PTP body. This is 12 bytes in size. And you split this into seconds, nanoseconds, and fractions of a nanosecond. And the seconds part you store in a 6-byte field. And the key thing is this won't overflow for a very long time. So it won't overflow until the year 8,925,512. So for anyone that happens to be operating with advanced archaic PTP technology in the 41st millennium, they won't have any trouble at all making these systems work. They'll still function even if they don't understand them. And it will be our very, very far future Star Trek people that will probably struggle a bit with PTP, perhaps. Or maybe not. I think Star Trek is much earlier than that. I don't think we have sci-fi. Maybe it's Star Wars would be a problem. Anyway, another digression. So then we have the nanoseconds proportion. This is 4 bytes. This doesn't overflow at 2 to the 4 times 8. It instead the hardware manually overflows it at 1 billion, because at that point that's equal to 1 second. Then you've got this fractions of a nanosecond part. This is a true fraction, so it's 2 bytes in size, so that gives us a resolution of 1 nanosecond divided by 2 to the 16. So that gives you an overall resolution of 15.26 femtoseconds, and it overflows when all these bits are equal to 1, so 0x FFFF in hexadecimal. So, message types, and also just how a protocol works. So we first announce messages, and these are used to build that PTP hierarchy. They contain information about the quality of the clock that sends the message, and it's split into class, priority, and qualities. And these are sent out constantly to all nodes on the network at some defined announced interval. And these are used in what's called the Best Master Clock Algorithm, or BMCA, which runs on every single PTP node. And what is this Best Master Clock Algorithm anyway? So this is what's used to build the hierarchy of clocks in the PTP network, and also to maintain it when changes occur. And this is quite cool because it makes PTP very dynamic. It automatically forms its hierarchy and fixes its hierarchy if, say, a clock goes down or is removed. So it operates in the following way. So every single node all the time, for every single PTP mode, is listening for announced messages. And if it doesn't receive any announced messages within some defined interval, it makes itself a master clock, and it starts to send its own announced messages at some defined announced interval. If a node receives an announced message that indicates a clock that's better than its own quality, then it stops sending its own messages and it makes itself a subordinate. If, on the other hand, a node receives an announced message that is worse than its own clock, then it does nothing. It stays a master, and it continues to send announced messages at some defined announced rate. And once the best node in the network has been determined, then this will, in the end, be the only node that sends announced messages. Every single other node will be silent. And the key thing is this algorithm does not stop. If, say, that grandmaster clock that's really, really good goes down, it's removed from the network, whatever, then other nodes will suddenly start sending announced messages, and the hierarchy will rebuild and the topology will change to account for the fact that master has been lost. And then there's the question of, well, how does it work out which clock is the best? And it uses a series of attributes to do this, and these are communicated within the announced messages, and they're prioritised in the following order. The smaller numbers are considered higher priority, so you go down this list, not up it. So first is priority 1, and this is a clock priority that you can manually configure. So you can use this to totally override the topology. If there's a certain clock that you just absolutely want to be at the top no matter what, you can use this. The next down is the clock class, and this is how traceable the clock is to absolute time. The lower the number, the better. So for instance, 6 means this grandmaster is locked to a primary reference clock. So this is a really, really good source of time. It's standardized to have an amazing holdover, and this is probably going to be the best source of time in the entire system, so you're going to keep to that. Then slightly worse, 7 is this clock is unlocked from a primary reference clock. I can no longer see this amazing source, but against other sources of time, its drift is being quantified to be within the specification that it's quantified against, and that's considered all right. So you'll probably still use that, but you won't use that if you've got a clock that is locked to a primary reference clock directly. Then 52 and 187, now you've got a clock that's unlocked. And not only is it outlocked, but also it's drifted beyond the amount that's considered acceptable. And then lastly, you've got 248, which is just a default. So your ordinary clocks will have that, for instance. And then the next is clock accuracy, which is quantification of the clock's accuracy in nanoseconds. Some will be better than others. Then you've got your offset scaled variance, which is a measure of the clock stability. And then you've got priority 2. So this is another configurable priority. So this is second order. So you can make things so that if everything else is the same, you still might choose one clock over another. And then finally, 6 is a clock identity. This is used as a tiebreaker. Every clock will have its own unique identity, and if nothing else matters, if everything else is the same, then it will just be picked based on the identity. And these are just some examples of clock classes in PTP. There are many others. There is a big long list. They're all in the standard and in other resources online. So then we get on to the actual synchronization itself. So we've studied this already. It's really the same. So the only difference is that now the packets have names. So remember in the previous lecture we were talking about the subordinate estimating its frequency drift with T1, T1 prime and T2 and T2 prime. The only difference here is that when the packet that gets sent out to the subordinate that's used to measure T2 and possibly send T1 and definitely used to measure T1, this is called a sync message. And if T1 can't be inserted into the sync message, it's sent separately, and the packet that's used to transmit that is called a follow-up packet. And it's exactly the same for when you send T1 to 1 prime. And the exact same thing before is that essentially the subordinate is aligning its clock to match the frequency and time of the master's clock. If they've also measured the delay using two-way timestamping, then this will also be used to correct the offset as well. And the subordinate, this is key actually, so the subordinate stores every new T1 and T2 timestamp between the sync messages. So what this means is its frequency is adjusted whenever a new synchronization or follow-up message arrives, and these are sent at some defined synchronization interval. This is really protocol dependent and profile dependent. Depends what specific time you've set, if you've got the opportunity to set it. In some profiles it might be set to a specific value. The other thing that's important to note here is typically there's a proportional integral controller behind this as well. So it's not just a simple case of like you will measure the offset and send something out. You'll smooth this over a period of time. So you've got a servo loop here typically, not just a simple I've got my correction between two timestamps, update your clock exactly this amount. It'll be more smoothed over time. So then delay measurement. So we mentioned delay measurement in two-way timestamping in the previous lecture. So this is how it's done in PTP. So there are two ways. So the first is end-to-end or E to E. And in this case, it's exactly the same as we went through in the first lecture. You measure the delay from a subordinate to a master. The second mode is a bit different, and it's also quite confusing when you actually look at it. In this mode, it's called peer-to-peer or P2P, confusingly very similar pronunciation to PTP. Here, the delay is measured between two nodes, irrespective of what type of clock they are, master, subordinate, transparent. Sorry, E to E is measured from a master to a subordinate. Sorry, shouldn't be that. But in the second type, it is always measured between two nodes, irrespective of what type they are. Not all of the delay measurements are used until the hierarchy changes. But the key thing is that both delay approaches assume that the transmission delay in each direction is identical, i.e. that there isn't any asymmetry between the two delays or paths. That said, sometimes you can enter a manual asymmetry value to compensate for asymmetry if you've happened to measure it. Say you happen to know the differences in fibre lengths between the two different paths, then you can enter that value and compensate for that asymmetry. So we'll go through this first approach end-to-end first, because it is pretty much the same as the previous method that we went through, just again packets of names. So we've already gone through our sync and follow-up packets. These are used to transmit T1 and T2, same way as before. But now we've got two more packets. So these packets that we went through in the two-way timestamping now have names too. So delay request is used to measure T3. It's used to measure T4 as well as this packet arrives. And then we have this other packet delay response, which is used to send T4 back to the subordinate. And just as before, we find the delay by solving for delay. We divide this all by 2, and we then, every time we get a sync message, we update the offset based on T2, T1, the delay that's been recorded. So the subordinate will be aligning the time of its clock using its offset adjusted for its delay after every single synchronization message arrives. And one key thing to note is that the master doesn't initiate the delay measurement. The subordinate does. And this measurement is repeated at some defined delay interval. One other key thing is that the sync interval and the delay interval don't have to be the same. They can be different. You can be sending sync packets at a faster or slower rate than your delay interval. You might only measure this delay and correct this D, say once a second, but you might send sync packets out 100 times a second. Well, more likely 128. It's up to the user how they configure the PTP profile. So now we get on to the second type of delay measurement. This is called peer-to-peer. And in this approach, we do things a bit differently. So we send 3 types of packets. So we've got P-delay request, P-delay response, and P-delay response follow-up. And the key thing is that in this approach, both the delay and the subordinate nodes are initiating path delay measurements. So the master is measuring the delay for itself, and the subordinate is measuring the delay for itself. And we do the calculation in basically the same way. So the subordinate is measuring the time at which it sends a P-delay request packet. The master clock then measures T4 as this P-delay request packet arrives, and then it measures T5 as it sends a P-delay response packet, and if it has time, it embeds T5 minus T4 into this packet. If it can't, then it instead embeds the T5 minus T4 within this P-delay response follow-up packet, similar way to how we have these follow-up packets with sync messages. Then the difference between T5 and T4 and the difference between T6 and T3 is found, difference between the two of those, and we divide by 2, that gives us a delay. And simultaneously, the master is doing the same thing, so it's calculating the delay too. However, and this confused me when I first looked at it, but I think presenting it this way helps. The master to subordinate delay measurement only becomes important if the topology changes. So if this is the master and this is the subordinate, you are just going to use these timestamps to calculate the delay at the subordinate. You'll use that value whenever you receive a sync message. You're going to correct your offset using D and adjust its time, same as the E2E approach. However, what if the topology changes? What if this master gets replaced by a better clock, say, and now this subordinate becomes the master and this master becomes the subordinate? Now it has the advantage that the topology can rapidly change because you've already measured the delay. You don't need to wait for the system to measure the delay again. So that is an advantage. Note that this is kind of the opposite way round to the previous calculation. If you were to sub in T1 to T4 into this, you'll notice effectively it's all been given a minus times by -1. So this is because you're measuring the delay the opposite way round. That's all that causes that. That's all. So then we have a bit more on these specific types of clocks. So first we've got boundary clocks. So these are a PTP device, usually some sort of switch or router that has multiple ports. The key thing is that it can act as a master and subordinate on different ports. PTP packets aren't sent through it like a transparent clock. The boundary clock instead is a source or endpoint for PTP packets. Usually it's a subordinate on a single port and it's a master on all the other ports. And a boundary clock synchronizes itself to a master on its slave port, and then it distributes time on all of its master ports. And this is how it looks in an actual system. So we've got some master clock running in E2E mode. We've got a boundary clock in the middle, and we've got a subordinate clock that's attached to this boundary clock. It's acting as a subordinate on this clock, and it's synchronizing its time and frequency with the master, and it's synchronizing its subordinates from its own clock. So we're doing our end-to-end time stamping here, gathering all our time stamping, changing our offset, measuring our delay, dealing with that, etc. And of course this is all ongoing all the time, changing our frequency and time, etc. Then PTP mode is also really quite simple. So the same thing is happening. The master's measuring the delay this way, the subordinate on the boundary clock is measuring the delay this way. Same here, delay here, delay here. And of course these path delay requests are taking place. In case the topology needs to change, it makes things able to rapidly reconfigure. And again, the boundary clock is synchronizing its time and frequency to the master, and it's synchronizing its own subordinates from its own clock. Then we have transparent clocks, and these get a bit more complicated. So the problem is, if you were to use normal Ethernet switches or routers in a PTP network, it compromises accuracy because these switches don't have control over the length of time packets remain in their queues at the input and output of these switches. So for this reason, we use transparent clocks or TCs in PTP networks. They don't act as PTP endpoints, so this means they don't synchronize their time to a master clock, but what they do is synchronize their frequency. And the key thing is they calculate the length of time, which is called the residence time, that sync, delay request and delay response packets take to travel through the transparent clock, and they add that time, the residence time, to the correction fields section of these packets. And unlike boundary clocks, transparent clocks handle these two modes, E2E and P2P, differently. In E2E mode, PT packets just pass straight through the transparent clock with the residence time added, and in P2P mode, the transparent clock calculates the delay between it and the master, as well as between it and the subordinate will calculate its delay between it and the transparent clock as well. So here's how these two modes work and look. So we've got our master clock, we've got our transparent clock with its input port and its output port, and well, I guess it's the other way around here, input and output, and we've got our subordinate clock here. So you can see our sync packet coming in, and it takes some time to pass through the transparent clock, and the transparent clock records this as the residence time, and if it is able to, it will embed the residence time within the outgoing sync packet. If it can't, then it will place this residence time within the follow-up packet. And the same is true for the delay residence time that's within the delay request. So the delay request comes back, the transparent clock records the residence time. It doesn't embed it in the delay request packet though, it keeps hold of it. T4 gets measured at the master, and then the master sends back its delay response, and the transparent clock embeds this residence time within the outgoing delay response packet going towards the subordinate. P2P mode ends up looking much more complicated. So what ends up happening here is everything is calculating the delays between itself and its neighbours. So we can really break this down. So we've got path delay requests from the master clock to the transparent clock, so we're measuring delay here. We're also doing the same here from the transparent clock to the subordinate. So these are taking place again in case the topology gets changed around. They're not used in this current form with this master here and this subordinate here. But if a topology does change and these swap places, these would then immediately be used and the other delay measurements would no longer be used. However, everything else is taking place. So we've got our delay measurement here, we've got our delay measurement here. The other key thing is that when we send through our sync packets, the transparent clock is embedding the residence time plus the delay that it's measured for this first leg. So it's measured the delay for this first part, and it puts that within the sync packet if it can, on top of the residence time. If it can't, then it will put it in the follow-up packet that follows that sync packet. And this just repeats every single time it passes through a sync packet. If you have multiple transparent clocks in a row, then they will just keep on adding their residence time and delay to these sync packets or follow-up packets. So then how do these compare? So why would you want to use one over the other? So let's spend a bit of time exploring this. So firstly, end-to-end or E2E. And the advantages of this really is that it works with legacy switches that don't support PTP. There aren't many others. However, it means that you can use this without ripping everything out of your network, so that can actually be a massive advantage, with, of course, an implication on the accuracies you can get. On the other hand, the peer-to-peer approach keeps your network load low, irrespective of whether you use transparent clocks or boundary clocks. It scales very well because if you've got lots and lots and lots and lots of ordinary clocks, your transparent clocks are measuring those delays independently, so you've not got as many packets which are needing to fly through to the ultimate master at the top of the system. The other thing is that every node measures the delay to its neighbours, so everybody knows the delays, so you can rapidly change your topology. If you need to put in a new master, you're there like that. The disadvantages of the two, though, if you're using end-to-end, if you're using transparent clocks rather than boundary clocks, then the issue is the grandmasters have got to service delay requests for everything, every single subordinate in the system. If you've got a lot of subordinate clocks, that can heavily load the network, and the grandmaster's going to have a lot of processing to do. For this reason, the scalability can be poor, and the other problem is you can't rapidly switch the topology because you need to wait for those new path delay measurements to take place. So you might temporarily be less accurate than you'd like to be. Then the disadvantage really of the peer-to-peer approach is that it's not compatible with legacy switches. Everything in the system needs to support PTP. There's no getting away with no support because then you'll be missing some path delay measurements in the system. So then we've got these two boundary clocks versus transparent clocks. Why would you use one or the other? So both act to increase the achievable PTP network size, but there are advantages and disadvantages of each. So with transparent clocks, there's no cascading of proportional integral control to tune with frequency, and they're also lower complexity, so you don't need a full PTP stack, you don't need any time synchronization, and you don't need any best master clock algorithm. The topology can be changed really rapidly, and as it comes to boundary clocks, the advantages are that you can have different delay mechanisms. So you could have on one port, you could be using PTP, you could be using E2E on another, and you can have different message intervals per port. You don't need to match all the sync rates, all the delay rates, etc. across the entire system. You can also lower the network load when you use E2E by dividing up the network into different chunks. And the other thing is that the boundary clock could become a master if the grandmaster goes down, so you've got redundancy in the system. As the disadvantages, for transparent clocks, the delay mechanism needs to be the same for every single port. You can't get away with changing things around, but it can't become a master because it doesn't have a PTP stack. It's not synchronizing its own time. so it can't switch over and go into a mode where it's acting as a master. It will always be essentially a slightly cleverer than a normal switch. With boundary clocks, your disadvantages are that your complexity is higher. You need a full PTP stack. It's got a clock in there. It's measuring time. You can also get a problem where if you have successive boundary clocks, the proportional integral control loops can become cascaded. You can get weird behavior resulting from that. The other disadvantage is you can't rapidly change your topology, and the last one is that PTP subordinates connected to the boundary clock can't choose which master. But on the other hand, that might be an advantage if you have someone that's connecting to your service, say that you want to not give visibility to the innards of your network, and if they use a boundary clock, then it means that your network is separated from theirs. So that's also advantageous. So then we have multicast versus unicast. So PTP can be configured to operate in either fashion. In multicast operation, every PTP node subscribes to some broadcast address, and that means that every single subordinate will receive PTP packets intended for every other PTP node on the network, as well as its own, because each switch is going to broadcast all PTP packets sent to it to every single port it has. So, for example, here you've got master clock, which is in blue. It's sending out its announce, sync, and delay follow-up packets. These are blue. It's going out to everything. And then you've got the specific packets going out to its red subordinate and its yellow subordinate. And what you'll see here is that the switch is sending out these yellow packets to the red server, but it's also sending out the red packets out to the yellow server as well. So unnecessary messages are being sent through this system. This can be a problem for scalability. If the message rate begins to get high enough and there are enough subordinates in the system, the network can become overwhelmed. In large networks such as data centers, this can become really serious, and for this reason in these networks multicast operation is often prohibited. However, it does have the advantage that it's simple, it's easy to configure, and there's no need to maintain state information in the system. There are no timers that need to be recording how long unicast packets can be sent to and from places. However, the opposite approach is unicast. This is actually optional in PTP. It is an optional feature under the standard. In unicast, every PTP mode only receives PTP messages sent to its specific address. So its MAC address in layer 2 or its IP address in layer 3. And the nodes negotiate time-limited contracts with masters for PTP messages with what we call signaling messages. And this enables the master to manage its own network load. The big advantage is that it's more scalable. So there's absolutely no issue with network load at the subordinates. You don't get this problem where you get lots and lots and lots of packets which are coming to you that you don't care about. But the disadvantage is that the master needs to maintain state information. So it needs to have a timer for every single subordinate that's requesting PTP message contracts. So what this can do is it can end up limiting the number of subordinates a single master can connect to. Eventually this does become a problem. There is another type you can do as well. This is called mixed multicast and unicast. So in this approach, announce, sync and follow-up messages, which are these messages which are sent from the master out to the subordinates only and not the other way around. These would go from the master to every subordinate anyway. So in this approach, which I suppose particularly well suits a network where every single server, say, is PTP enabled and cares about getting accurate time, you might not care if this is operating in multicast fashion for these messages. And all the other messages in the system, these are unicast, so the rates of these have to be negotiated. So yes, in unicast you'll see that these yellow packets are no longer being sent to the red server and the red packets are no longer being sent to the yellow server. So then just let's have a quick summary of the different PTP message types. So first is announce message. So this is a general message. It's used to build and maintain the PTP hierarchy. Then we've got sync messages. These are used for one-way time and frequency sync. They're part of two-way frequency synchronization, two-way time sync, and they're used to measure T2, and if possible, they're used to transport T1. Then follow-up packets are a type of general message, and they transport T1 if it can't be inserted somehow into the sync message. Then you've got delay request packets. These are event messages, and they are only in E to E modes, and they're used to request delay measurement and also used to measure both T3 and T4. Then you have the delay response message. This is a general message. It's not used for timestamping, that's why it's general. It is also E2E mode only, and it transports T4 to the subordinate after the master has measured it. Then you've got P delay request. This is an event message. This is P2P mode only, and it requests delay measurement. It's used to measure both T3 and T4. Then you've got P delay response, another event message. This is used only in the P2P mode. It's used to measure both T5 and T6, and if possible, it transports the delta between T5 and T4. And lastly, you've got P delay response follow-up, a general message, not used for timestamping, which is used only in P2P mode, and it's used to transport T5 minus T4, i.e. the delta between them, if that can't be inserted into the P delay response message. Then there are lastly two more types. There are signalling messages, which are used to negotiate optional P2P services, such as, for instance, unicast. And there are also management messages, which are also general messages, and they're used for monitoring, configuring, and maintenance. So then we get profiles. So these can be very confusing. PTP comes in lots of different flavors or profiles to tune the protocol. So these tune the type of delay mechanism you use, they choose the message rates you use, they tune whether it's layer 2 or 3, they tune whether it's unicast or multicast, and ultimately they're usually standards that build on the main IEEE 1588 profile, main 1588 standard, so the main PTP standard. And they're all built to suit specific applications. As different applications will have different requirements. So some of the most relevant to data centers are probably IEEE 1588 default profile. So this is the PTP profile, so it is the default one in the P2P standard, and it's for generic use really. It has very few restrictions, and it is extremely flexible. It uses layer 2 or 3. By default, it uses multicast, but you can use unicast optionally, and you can use end-to-end or peer-to-peer delay measurement. No problem. Then you have the Open Compute Project Data Center Profile. So this is a profile specifically intended for data centers. It is layer 3 only as a consequence of that, because generally you will not be operating in only one, well, you definitely won't be operating in one subnet in a data center. It is only unicast, not multicast, because in many of the big data centers, multicast is a potential disaster, because you've got so many places packets might be spit out to. It only allows transparent clocks at the moment, but there is a future approach with boundary clocks at each switch or router that's been proposed. And you must use end-to-end delay measurement in that approach. Then there's the IETF Enterprise Profile. This is intended for enterprise data centers, so especially the finance industry. It's layer 3 only. It uses mixed multicast and unicast, so what that means is the announce, sync and follow-up messages are sent in multicast fashion and everything else is unicast. It allows both transparent and boundary clocks, however you must only use end-to-end delay measurement. Then you've got the ITUT G.8275.1 telecom profile. So that's intended for mobile cellular networks. And so that includes data center processing for backhaul in particular. It can include that, but it's predominantly targeted at synchronization of base stations, etc. in time. So it only operates in layer 2. It only allows for unicast. Multicast is not permitted. Transparent clocks also not permitted. And end-to-end delay measurement must be used. There are many other standards and profiles. There's the C37.28238 power profile, you've got the utility profile, you've got the IEEE 802.1 AS profile, etc. Lots and lots. And you can find a list here if you'd like to check them. So just to conclude, we explored the different types of clocks used in data centers. I'll just move my face out of the word conclusion. And we explored the different types of clocks used in data centers, telecom applications, as well as metrology, and their rough respective performance. I wasn't able to show an Allen deviation plot, but maybe in future I might edit things to include that. I'll include a link to that actually. That would be viable. We explored the different contributions to accuracy and precision in time synchronization protocols. We explored the main time synchronization protocols that are common commercially, especially in telecom and data center networks. And lastly, we covered the precision time protocol, or P2P, which enables nanosecond to microsecond synchronization accuracy, predominantly in local area networks, although you do sometimes see it in some WANs. That's the end of the 2 lectures that I have prepared on time and clock synchronization. So thank you for listening, and I hope they will be useful if you are interested in the time synchronization industry.